So, we were talking about the currents and specifically current density, and if you have a volume in which the current exists, then in that volume some charges are moving, crossing a particular cross section or an area, and then how much charge crosses in how much time, that defines current, and then through which area you are making the calculations, divide by that area, and then it becomes current density. So, we denote the current density by the letter J. It is a vector quantity, it has a direction, it has a magnitude, and it satisfies all other requirements of being called vector. Only direction and magnitude is not the sufficient criteria for a quantity to be a vector. There are other things also, specifically how the components transform as you go from one frame to some rotated other frame. So, all those things are there that we will not talk, but this is a vector quantity and we wrote it in terms of the charge density and V. So, this is known as volume current density. This is known as volume current density. Why? Because all these charges which are moving, they are distributed in a volume, and therefore, it is known as volume current density. This is the volume charge density, and what does that mean? This is, you take a small volume and see how much is the charge. Which charge? Only the moving charge, the flowing charge. If there are other charges which are stationary, then we do not have to take that into account. So, the volume charge density which is moving, and this is of course the velocity of the charges. And we said, as we said, this is a point by point relation. It is defined for a specific point. If you have a volume and in the volume you have a point, and you can ask how much is the current density here, how much is the current density here, just like pressure. If you have water in a bottle or in a beaker or in a bucket, then you can ask what is the pressure of water at this point. So, what do you do to get that pressure? At that point you construct a small area and then see how much is the force on it, divide by the area to get that pressure. So, something like that. If you have a volume and at this point you want to know how much is the current density, then you construct an area here around this point and then ask how much is the charge crossing per unit time dq by dt through this constructed small area. And then we do this, if this is the velocity and the charges are going this way, and then we ask how much is the current density, and then this rho v etc. work out. So, it is a point by point you can ask how much is current density here, how much is here, how much is here. Whereas current, if you look for current, then you give me some area, bigger area or whatever, and then you can ask how much charge has gone from this side to that side. So, that is on a area and this is on a point. So, it is a point by point function. So, this we talked about, and let us take an example. Suppose we have, just consider that this is a cylinder, and in this cylinder actually we have salt, we have rock salt here, and suppose each grain is charged. So, that in this entire cylindrical volume you have a uniform charge density, right. All this salt which is there, each grain, suppose somehow I make them charged and then fill it. So, this whole volume is filled with the charge, and if it is all uniformly distributed, as it is, all the salt is here uniformly distributed, and if it is also uniformly charged, then you have a uniform charge density in a cylindrical volume. Now, suppose I rotate this about its axis like this, I rotate it about its axis with some uniform angular velocity omega. So, entire charge is moving. Is there a current? Yes, there is a current. Take any area inside this, take any area, and the charge is crossing that area, and so there is a current, volume current density. So, how do I get this V, the rho I have charged it, I know how much is rho, and then omega I know, omega is same. If it is making one rotation in say 0.2 seconds, then I know how much angle it is rotating per second, and so omega I know. What is the velocity? Velocity of any point you take inside this whole volume, and what is the velocity? So, at different points the velocity will be different. At the surface the velocity will be largest, speed will be largest, and close to this axis of rotation the velocity will be smaller. At the axis of rotation this velocity will be 0. Okay? And then if you have this cylinder which is rotating about its axis with an angular velocity omega, and then you have a point which is at a distance s from this axis, a point which is at a distance s from this axis, perpendicular distance s, then this velocity speed will be s times omega. And what will be the direction of this motion? It will be tangential to the circle in which that particular point is moving. We call it phi direction, phi cap direction. And so, velocity will be s omega phi cap. We will just explain what it is. Let me complete this. So, the j will be rho, then this omega s, and then phi cap. This is the current density. At any point you pick up a point and ask how much is the current density. I will ask you at what distance from the axis is this point, that is s. I will multiply by omega, multiply by this rho charge per unit volume in that, and then I will put up this direction that okay, this is the direction of velocity, and therefore this is the direction of current. Now, what are these s and phi cap? I am using cylindrical coordinates, cylindrical polar coordinates in full, but mostly I will be calling it cylindrical coordinates. You must be familiar with this. In part 1 of this course also I had introduced spherical polar coordinates and cylindrical polar coordinates. Just to revise, you have x, y, z axis, you have x, y, z axis, say this is x axis, this is y axis, this is z axis, and you take any point in the space, not in the plane of the board. The way it is drawn, this plane of the board is yz plane, but you can have points outside the board also or on the other side of the board also. So, this point is not necessarily on this plane. So, from here you drop a perpendicular on this z axis. So, suppose this is the perpendicular, it does not look like perpendicular because this point may be somewhere else, this point may be somewhere here, and from here I have to drop a perpendicular. And you drop a perpendicular on this xy plane also, this horizontal plane also, and then if you join, you get a rectangle, you get a rectangle. Now, this distance is s, this distance is s, this distance is z, which is same as this z, and this angle is phi. This angle is phi. S, phi, z. So, there are three coordinates S, phi and z. If a point is given, x, y, z axis are chosen, drop a perpendicular from the point to the z axis and see how much distance it is, that is S. Then drop a perpendicular from this point on the xy plane and the foot of perpendicular is joined with the origin, and angle between the x axis and that line is phi, and z is of course how much above the xy plane it is. So, when you draw the perpendicular, this OZ will be small z, or you can also say that what is the distance of this point from the xy plane, that is z. So, these are three coordinates S, phi and z. So, now you can appreciate this diagram better. Here is a point, I drop a perpendicular on the z axis, I drop a perpendicular on the xy plane, and then I get this rectangle, and this line here on the xy plane makes angle phi with the x axis. So, from phi equal to 0, which will be this xz plane, I rotate this whole plane and then I increase phi of those points, and in the direction in which the points are going on rotation, that is the phi cap direction. So, if it is going in a circle like this, and here the velocity is in this direction, it is going in a circle like this. So, if I draw it here, if I draw a circle like this, here this is phi cap direction, 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 this is phi cap direction, like that. When you rotate about the z axis, then the tangential direction is phi cap direction. So, from point to point, that phi cap direction will change. It is a unit vector, it is a unit vector corresponding to this coordinate, but then that unit vector will change direction as the value of this phi changes and it rotates. So, that is one. And similarly, you can define S cap direction. This is S cap direction, the direction in which S increases. Okay, the direction in which S increases, this is S. So, if I just have to increase S, extend this line in this direction, it will go in this direction, that is S cap direction. And Z cap direction is vertical, of course, the direction in which Z increases, that is Z cap direction. So, S, phi and Z, these are the coordinates. I am using S, DJ Griffith also uses S, so I have taken it from there only, and phi and Z I have already told everything. So, corresponding to this S coordinate, we have a unit vector S cap, corresponding to this phi coordinate, we have a unit vector phi cap, and then corresponding to this coordinate Z, we have a unit vector Z cap. Now, since the rotation, since that whole cylinder was rotating about its axis, all those grains, all those rock salt particles, all those charges, they were going in that circles around the z axis, and therefore, the velocity direction is phi cap, and the magnitude of velocity is omega, angular speed multiplied by the distance from the z axis, which is also the axis of rotation, and then the charge density. This is the expression for volume current density. There is another word which will be used, and this will be volume current element. What is that? You have certain volume and the current is there and the charges are moving. The charges are moving, the current is there. In this volume, you take a small volume which will be written as d tau. This is the Greek letter tau. So, whenever we talk small volumes, our symbol will be d tau. So, in this volume, how much is the how much is that current, looking at that, this current here, this current here, how much is the current in this particular volume, that is known as volume current element, and that is J d tau, volume current density, and then multiplied by that small volume. So, that is our current element. So, we will be having a current in a bigger volume, and maybe suppose I need magnetic field at a certain point due to this. So, we will first pick up a current element, and because of that current element, because of that small volume in which the current is there, for that much of current, what is the magnetic field, and then we will integrate. So, we will need this concept of volume current element. For example, in this wire, suppose you have a wire and in that wire current is going. So, I need magnetic field due to the entire wire, entire circuit. In an isolated wire, you can have that like I rotated about the z axis, but if it is a circuit, then this all that current which is there in the circuit can produce a magnetic field. So, I have to get the field from small elements, current elements, and then add. So, this will be needed. Another concept which I would like to introduce little bit is that we are using volume current element, volume current density, like that. We can have current only on the surface of a material, only on a surface, that is also possible, and correspondingly we define surface current. If the charges which are moving to make that current, if they are all distributed in a volume, we get volume current. But if the charges which are making that current, if they are on a surface and on that surface only they are moving, then the current is called surface current, and correspondingly we will define surface current density. How do I define that? Suppose here is a surface. Now, I have a surface. Suppose this is a surface, and then there is charges are there, and those charges are moving. Right? This is just a surface. It's not a volume. It's just a surface. Suppose this table or this board itself this is a surface, and the charges are residing on the surface of this board, and then the charges are moving on this surface only, right. So, you do not have a volume as such. You do have, all materials have volume, but then we neglect the thickness. The thickness is so small, maybe some 10, 12 molecular layers, and we are always talking in millimeters and centimeters. Okay. So, we neglect that. So, if you have that kind of current, that is known as surface current, and to get that current density, what I do is I take a length on this surface perpendicular to the direction of this charge flow. At different places different directions will be there, may be there, and therefore, you have to take a small element dl. This is a small element dl. Okay. Line, this is a line on the surface, and then you ask how much charge has gone past this line, how much charge has crossed this line from left side to the right side or right side to the left side. So, that will define the current. First you define the current. How do you define the current? How do you define the current? You define the current by saying, asking the charge dq crossing what? Crossing the line dl. The line, there is a line of length dl on this surface, and I have drawn it perpendicular to the direction of those charges motion of those charges at that location. At different locations, maybe the speed v can be different or the direction can be different. That is why at every point it will be different. So, what at whichever point you want to define this surface current density, there you construct this dl, and there you see what is the direction of velocity perpendicular to that. Okay. So, how much charge is crossing? dq crossing time this line dl, line of length dl in time dt. That is our current, dq by dt, that will be our current. And that current divided by this dl. Okay. Total how much charge has gone from this side to this side per unit time, that is the current, and that current divided by this length dl is known as surface current density. So, if this current is say delta I, then this delta I and divided by this dl or delta L, that will be known as surface current density. And the symbol for that is K. The symbol which we will use for surface current density is capital K. The magnitude of this surface current density is current divided by the length that you have taken to calculate the current, and then the direction of this K is the direction in which the charges are moving. If they are positive charges, if you have negative charges, then opposite to that. So, that will define you surface current density. Now, we had shown that you have if you have a volume and you have an area, and then if charges are there and they are moving with velocity v, then this j was rho times v. This was for volume. For surface, if you do the similar analysis, you have a surface and on that surface you have a line dl, and then you ask you have a surface charge density which we will write as sigma. So, sigma is surface charge density. And how I define that? How do I define that surface charge density? I take a small surface area, the entire charge is distributed on a surface, big surface, and on that surface I take a small dA and then ask how much is the charge in that dA, and that charge divided by area will be surface charge density, which we will write as sigma. So, sigma is the charge density, and once again they are all moving with velocity v. Once again, if I take this rectangle now of length v dt, this is a rectangle, dl is the width and v dt is the length, v is the velocity with which the charges are moving. Similar analysis, whatever charge is here in this rectangle at some time t, in next time dt, this entire charge will cross this dl. So, from there you can calculate how much the current and then how much is the current density, and what you will find is this k is equal to sigma v, and put a vector sign. So, if you know the charge density sigma and if you know the velocity with which they are moving on the surface, then you can immediately write that this is the current density, and this k and dA, this will be known as, this is called current element, surface current element. Keep comparing. When it was volume current element, it was J d tau, J d tau. This was your volume current element, right. So, it is volume here, it is surface here, it is volume current density here, it is surface current density here. So, you know what is going to come next, it will be linear current density.